around. So Stats Central, we offer free design advice to UNSW researchers, and also with analysis help for HDR students, grant reviews, short courses, monthly seminars. We can be consultants or be work with contracts. We have an upcoming course next week, next Wednesday, Introductory Statistics for R. So that's, from August 31 to September 2, 9 to 3. And it's going to be hybrid, so in person, but also some people online. So things like logistic regression, linear regression, and so on. We've got some other events coming up as well. So some short courses, which I mentioned one of them just then. We've also got Introduction to Regression, September 5th to 8th, to talk about in a second. We have Hacky Hour, that happens every Thursday for 1 hour. And we have, there's a UNSW code or R user group, which happens on the first Monday of the month and the third Monday of the month. Okay. So we have this Introduction to Regression modeling in R on the September 5th. So this is a little bit more advanced. More complicated regression models, including splines, interactions, model selection, generalized linear models. So hopefully that will be of interest. And that's it. So Eve, are you ready to go? If Eve is there.
Hi, Nick. Sorry.
Hey.
I'm here. My computer has just doing that thing that I'm sure all of us have experienced now, where the video is not showing, even though I've got it turned on. So that's really annoying. You know, I think I'm just going to give the talk because it's mostly looking at slides anyway, and I don't know how to fix this problem.
Yeah, that sounds good. I think we'll be looking at the slides anyway, so yeah.
So I'm going to share my PowerPoint. Start the slideshow. Great, thanks everyone, and I'm so sorry that you can't see me, because I know how awkward that is. So yeah, this course is a friendly introduction to ordinal regression, and I hope it's going to be really friendly. So I picked this topic basically because a lot of people do have ordinal variables, and it's quite a extension in concepts to the kinds of regressions that you've probably come across before, like doing a linear regression or analysing a count variable or a binary variable. Ordinal regression is another level of complexity, and so I really just want to cover the concepts behind this, because they are a bit tricky, and once you've got the concepts, then you'll be able to go forth and analyse your ordinal regression, ordinal variables with whatever your favoured software is. So I'm going to cover what ordinal variables are, how do you visualise them and their relationship with other variables, and so just the concepts here, and then how we can model them and their relationship with other variables. And so I want to go through how to understand the coefficients that you get from ordinal regression, and also how to check the assumptions. I'm not going to cover how to do everything in code, just because it would take too long, and I really just want to nail the concepts here. And if you want additional support with that, we can always go through that at another time. And yeah, I'm also not going to cover how to implement everything in every software package under the sun. You know, as Adam Bant would say, Google it, mate. But once you get a good understanding of what the software packages are doing, then you'll understand how to interpret the output. So, what are ordinal variables? Well, here's a classic one. It's a kind of a Likert scale satisfaction rating. So anything that is anything that's categorical and the categories have an ordered structure to them is an ordinal variable. So with a Likert scale, it often goes strongly disagree up to strongly agree. And these are like categories, like whether you agree or whether you disagree, but they do have this ordered nature. So here's another example. This is the blackleg disease severity rating scale. So this is a disease that affects canola. And you know, you can see that they've come up with this rating of from 0 to 5, and they've got this, you know, visual metric on how to like rate it into one of these categories. And disease severity scales are a very common one. You know, we never have enough bananas in stats talks. So here's another ordinal scale that agricultural industry is interested in, the how to rate the maturity of bananas, and that they might use this. They might try to, you know, optimize their banana crops and when to pick them and stuff. That's why they might be analyzing this variable. And a final funny one is the hats on from the Good Food Guide. So I'd say this is an ordinal variable. It's probably got 4 categories because a restaurant can have no hats, 1 hat, 2 hat, 3 hat. I don't know if anyone actually does regression on the Good Food Guide, but you know, you could. So for this talk, the example I'm going to use is coronary artery disease. So I found a data set that has looks at the severity of coronary artery disease. And so they determined this using angiograms, and the scale goes from 1 to 4, where 1 is no disease, and then 2, 3, and 4 are increasing severity of coronary artery disease. And this data includes 294 patients that underwent angiography in Hungary. And I got it from the Ordinal Forest package in R, but the original publication is attached to the slide. It's from the American Journal of Cardiology. So you can see that in this data set that we're going to use a lot, so I'll just take a bit of time to go through it. The majority of the patients, so like 180 of them, are in category 1 with no disease, and then you've got some patients with increasing severity of coronary artery disease. So if we wanted to look at the distribution of this response variable, coronary artery disease, we could do the stacked bar, or you could also plot the bar chart with the bars separated, and then you can see sort of how it's skewed out. You know, most people in the no disease category, and then this tail here of people in 2, 3, and 4. So if we want to look, so I'm kind of going through how to visualize the data. If we want to look at whether coronary artery disease is associated with another categorical variable. And so here I picked sex. So there's males and females in the data set. One thing you can do is to plot side-by-side bar plots where the bars are stacked with the colors determined by the classes. So, here you can see that it looks like males are more likely to be in classes 2, 3, and 4, whereas women are more likely to be in class 1. So that I just sort of, there's some alternative visualizations that you can do for visualizing an ordinal variable versus another categorical variable. So as well as the bar plots, you could also try a heat map. This is presenting the same information in a different way, where you color the heat map by the proportion in that class. And if you look at it, you can see females that they're most likely to be in class 1, and so are males, but less likely than females. And the final plot that you could use, depending on your audience, is this alluvial plot. So some audiences might like this plot. It sort of shows here you've got your males, and these widths of the bars show this is the proportion going into class 4, 3, 2, and we got a lot here in the yellow going to class 1. And then the females, we've also got a lot going to class 1, and we've got these thinner rivers of people going into classes 2, 3, and 4 from the females. So some people like these alluvial plots and find that a good way to get the information across. I would just say experiment and see what looks good on your data set, what's conveying the message the best, because the alluvial plots can look a bit messy if you have a lot of categories. So another should say, if questions pop up, feel free to butt in and let me know, Nick, but otherwise I'll just keep talking. So another variable that is in this data set from the Hungarian angiograms is old peak. So I thought I'd talk through how we can visualize the relationship between an ordinal variable, that's our coronary artery disease class, and a continuous variable. So here, old peak is actually, it's the height of this ST depression. So they do an electrocardiogram, you get this graph, and they measure this depression, and it's after exercise, and this old peak is a could be diagnostic of coronary artery disease severity. So if we wanted to visualize this, so it's a continuous variable, we could plot a ridgeline plot. So this is a kind of plot that I've recently gotten a little bit of a fan of, I've become a fan of. So here it just plots the distribution of the data along old peak for each class. So you can see that in class 1, the no disease class, most people have an old peak measurement of 0, and there's a bit of a tail here. And if you go up to class 4, like the mode is at 2 for the old peak values, and you've got some very large old peak values too. And it's sort of seems to be slowly shifting to the left. So it looks like there's a positive association between that old peak score and what disease class you're in.
Or Eve, there was just a question there on what program was being used.
Yeah, so I have made all these plots in R, in ggplot, and when the slides are provided, I'm happy to provide all the code that I used to analyze this data set, like this freely available data set that you can all download yourself and generate the plots and the models as well. So yeah, this is all R ggplot. I think this is an extension for ggplot called GG ridges, I think. Or if you Google ridgeline plot for ggplot, but it's a alternative to box plots. So I'm now going to show you the box plot version of that ridgeline plot. So same information, it's just looking at the distribution of old peak in each class. And again, you can see that it looks like the larger values of old peak are associated with more severe disease classes. And yeah, any software should be able to do your box plots. And yeah, like this line here is the median. So you can see in disease class 4, the median old peak score is 2. And people with high old peak scores are nearly always in the highest disease class, or at least the upper 2 disease classes. You could also experiment with violin plots. There's another version of box plots. So I can see the chat going wild. Do I need to stop, or yeah, or is that being answered there? Yeah, okay, cool. So now I've covered what ordinal variables are and how we visualize them and their relationship with other variables. So I now want to move on to how we model ordinal variables and their relationship with other variables. And I'm specifically going to be talking about this model called a cumulative link model today. So just going, why is my thing not working? Yeah. So I just first want to cover like why you should use a cumulative link model over other alternatives. So just a few things that you might come to mind is you could convert your ordinal scale to a numeric scale. So I could just use the 1, 2, 3, 4, and I could analyze that. So this is not a good idea in general. It's when you do that, you're trying to estimate the mean category, and it doesn't really make sense to estimate the mean across categorical variables. The numeric scale that you apply to these ordered categories is arbitrary. So you've applied a linear scale, but you could also apply like a quadratic scale or a log scale to the numbers, and you'd still have that same order. And so, yeah, it just doesn't really make sense. Another option is to treat the variable as categorical and ignore the ordering. So, just treat it as a classification problem. I'm trying to classify each observation into one of the categories and use any old classification algorithm. So this is generally just not as powerful as taking the ordering of your data into account. And by not as powerful, I mean that you're more likely to make classification errors and get things more wrong than if you you take the ordering into account. So I'm now going to go through the cumulative link model. So here's what we're aiming to do. We're aiming to estimate the probability of each observation belonging to either class 1, class 2, class 3, or class 4. So, and we're going to estimate these probabilities P1 hat, P2 hat, P3 hat, P4 hat. So we're going to do this, and I know this looks scary, but I'm going to really try and talk through it by estimating the cumulative probabilities of belonging to class J or lower. So we're going to try and estimate CP1 is the cumulative probability of belonging to class 1 or lower. So that's just P1. CP2 is the probability of belonging to class 2 or lower. So that's P1 plus P2. And CP3 is the probability of belonging to class 3 or lower. So that's P2 plus 3P plus P1. Yeah, I can't remember if I said the right things then. So, like to just plot that out, you've got your data here, and the height of each of these bands is basically relative to P1, P2, P3, and P4. And so CP1 is P1, CP2 is P1 plus P2, CP3 is P1 plus P2 plus P3. And I haven't said anything about CP4. Can anyone tell me what CP4 is? And why I might not care so much about it? This is just to check that you're following. I'll see if something's popping up in the chat. You can put it in the chat. 1, 1, 1, 1, 1. Yes, exactly, or 100%. So yeah, CP4 is the probability that you belong to any of the possible categories, which is of course 1. So hopefully you're all still with me, because now I'm transforming the cumulative probabilities. So instead of estimating the cumulative probabilities, what we're actually going to try and do is estimate the cumulative probabilities on a log odds scale. So the odds transformation is CP1 over 1 minus CP1, and logging that is called the log odds. So I'm taking the log odds of each of my cumulative probabilities, and that's the quantity that I'm going to work with ultimately to try to get back to these original probabilities, P1, P2, P3, and P4. Any questions? So that's all fine, but we want to add we want to add regression in. So we're going to regress these quantities on our explanatory predictors. So now we're going to add in our explanatory predictors. So let's just start with one predictor, x1, and the regression equations for an ordinal regression look like this. So the first one's theta1 minus beta1 x1. The second one is theta2 minus beta1 x1. And the third one is theta3 minus beta1 x1. So if we had no predictors, we just have these thetas, they're like intercepts, except it's kind of weird to talk about intercepts. So we call them thresholds. Theta1 is the log of this quantity, this function of CP1. Theta2 is the log of this quantity, and so forth. So they give the cumulative proportions on the log odds scale. But adding in these predictors, what we're doing here is estimating the effect of x1 on the probability of an observation moving into a higher class. So I'm going to try and illustrate that on the data. Sorry, first of all, I'm going to do that in a minute. So if we only had 2 classes, this actually collapses to binomial logistic regression. So we have 2 classes, class 1 and class 2, and we're modeling the log odds of being in class 2, which is actually log P2 over 1 minus P2. And now because P1 plus P2 equals 1, we can just reverse this. So it's the log of 1 minus P1 over P1. Now we know that P1 is the same as CP1. The cumulative probability of being in 1 or lower is the same as the probability of being in 1. And then that, that equation is minus theta1 plus beta1 x1. So that's the negative of this. Minus theta1 is the intercept in a classical logistic regression, and beta1 is the slope in a classical logistic regression. So now is where it gets complicated. So now we're estimating. We've got 3 equations, but we're still only estimating 1 regression slope, beta1. So these are the same. And that's, I guess, the really important and powerful assumption of the cumulative link model. It's called the proportional odds assumption. And I've also seen it called the parallel regression assumption. That should, and they, the reason this assumption is important is that, well, it allows you to have a single effect of your predictor on your response variable. Because if you had different, like say you gave these betas each their own names, so beta 1 here, beta 2 here, and beta 3 here, then the effect of your predictor variable on your response, you get 3 different effects. And some might be positive and some might be negative, and then it's really hard to interpret. So this proportional odds assumption, it makes your results really interpretable. It means you can say, like, there's one effect of this this predictor variable on my response, and here's what it is. Of course, it's an assumption, and you do have to check that it makes sense to be able to do that. So to just illustrate what the beta 1 is doing, like if you were looking at the predictor variable sex, and it's 1 if sex is female and 0 otherwise, then beta 1 is the estimated difference in the log odds cumulative proportions between males and females. So these, so if you just call this thing the link function, then this is the inverse link of beta 1 in males, because they're kind of like, males are the intercept in this model. Theta 2 is sort of this high and theta 3 is this high. Then the difference between males and females is given by beta 1. So the difference in class 1, you go from here to here, and that's given by beta 1. And the difference in class 2, you go from here, this height of cumulative proportion up to here, that's given also by beta 1. And you go from this height here for class 3 up to here, so the probability of being in class 3 or lower, and it increases here also by beta 1. So in this model, can anyone, just to check that people are following, do you think beta 1 is going to be positive or negative? And I'll look in the chat for some responses. In terms of the way that going from the difference between females and males, do you think that that female dummy variable should have a positive or negative coefficient? People are really confused. Negative, yeah, because excellent, and it's tricky. So what's happening is that the difference is positive, but because we've got a negative here in front of the beta 1, we need to like do a minus so that the overall cumulative probability increases for these lower classes. So that's why there's a negative. So that's why the equation here has a negative in it. It's so that the way we interpret the regression coefficient is the chance of going into a higher class. So if you're female, you have a lower chance of being in a higher class, and that's why the regression coefficient will be negative. So it means you're less likely to have severe coronary artery disease. I've maybe overdone the examples, but here I'm going to look at old peak, just to give you an idea of how we interpret it if you've got a continuous variable. So as if old peak is 0, you might have this distribution of people in the classes. And then if old peak is 1, the distribution shifts to the right-hand side distribution of people in the classes. And so you can see in 1, like you've got far fewer people in class 1, and then it's decreasing cumulative probabilities. So here, is beta 1 positive or negative? Positive. Thank you. So yeah, so just to talk that through, as old peak increases, we saw in the visualization that as old peak increases, your chance of being in a higher disease severity class seems to be higher. So we want to talk about that as a positive slope. And so you get a positive estimate for beta. And I guess that's why when you see cumulative regression equations written out, they've got a negative here, but that's just to reverse everything so that it's in the intuitive explanation. So we want to estimate this, this cumulative link model in R with the ordinal package. So these are the equations. I'm going to try here to estimate the relationship between coronary artery disease class with sex and old peak. So put 2 variables in there. These are the 3 equations that it's going to try to estimate, to solve. And we solve these equations using maximum likelihood. And we just try to estimate the parameters theta 1, theta 2, and theta 3, and beta 1 and beta 2, which make our data most likely. So I've just picked one package that does this, but you know, there's many ways to there's many packages that use maximum likelihood to estimate the same model. So in Ordinal, you just give it a regression equation. I want class to depend on sex and old peak, and it fits the model. And this is the stuff that it spits out. And the stuff that it spits out should be similar across packages. So it gives me here these threshold coefficients. So these are the thetas, theta 1, theta 2, and theta 3. And they are, generally not that interesting, and we generally don't care about them, but they're just, they're like intercepts, so we need them in the model. I've also got my betas. So I've got my effect of being female compared to male, and my effect of old peak. And you can see, as we expected, the coefficient for female is negative, so less likely to be in a severe disease class than males. And the coefficient for old peak is positive, meaning as old peak increases, your probability of being in a higher disease class increases. I've also got p-values, so that's just testing whether these coefficients are different to 0, and that's doing a Wold test. So if you've got a smaller data set, these Wold tests are known to be quite approximate, and they can be quite off. So a more accurate test you could do is a likelihood ratio test. So if I wanted the p-value for old peak, I might fit a model with old peak in there, fit another model with old peak not in there, and then run the likelihood ratio test. So in R, you can do this with ANOVA, and it takes the difference between the likelihoods as the statistic, and we know that asymptotically this has a chi-squared distribution, and so we get this p-value here. It's a very large likelihood ratio statistic, so it's very likely that old peak is explaining some variation in the data. I forgot the confidence interval slide. Oh well. So what about the proportional odds assumption? So recall that it's a key assumption that the effect of sex and old peak on the probability of changing into a higher class is the same no matter which class you're in. So we've got this proportional odds assumption. It's kind of tricky to check this assumption. Some software packages do offer tests for this. There's this one called the Brandt test, but these have been shown to reject the null hypothesis overly frequently. So if you do run these tests, a lot of the time they'll tell you, oh, it doesn't satisfy the proportional odds assumption, but they do it a bit too much. So I'm going to demonstrate a graphical solution for checking the proportional odds assumption. And this is the one recommended in this Frank Harrell book. And slide. So the graphical method, if you think about these 3 beta 1s, the assumption is that they're the same. So what if we fitted 3 separate binomial GLMs, one to estimate the probability of y being less than or equal to 1 versus bigger than 1, one to estimate the probability of y being less than or equal to 2 versus bigger than 2, and one to estimate the probability of y being less than or equal to 3 versus bigger than 3. So then if we did that, we'd get 3 estimates of beta 1. and we check that they're similar. That's the graphical solution. So I've done this on my old peak, coronary artery disease data. And these are the 3 coefficients I got for old peak. But when I split the data at each of the 3 cut points and the 3 coefficients for sex. And I added the confidence intervals on because they are also estimates from a GLM. And once I've got the confidence intervals on there, I'm pretty satisfied that the slopes are fairly similar. Like they are a little bit different, but they're enough the same that I'm happy to make this proportional odds assumption. Did that make any sense? Hopefully. So you can also try the Brandt test, but just be aware of its tendency to reject the null hypothesis a bit too much. We also need to assess the linearity assumption. So when you do a regression, you're assuming like a linear relationship between the link function, so the log odds of the cumulative probability, and say this continuous variable old peak. So we can plot the residuals versus fitted. I remember that linear regression first year stats, but how do we calculate residuals and fitted values when we've got 3 predicted values for each observation? So for each observation, what you actually do is predict the probability of being in class 1 or lower, in class 2 or lower, or class 3 or lower. So you don't even have one set of predicted values, and you also don't have one set of residuals. So there's been recent work, like about 10 years ago, no one had a satisfactory definition of a residual for an ordinal regression. But more recently, there is development that's developed these things called surrogate residuals, and we can plot the surrogate residuals against these fitted values. And there is software that gets these for you in R. So I plotted the residuals against the fitted values, against the predicted probabilities of being in each class. So this first residual plot is the surrogate residuals versus the probability of being in class 1. And now the second plot is the residuals versus the probability of being in class 2 and 3 and 4. And so, it's kind of annoying, like you don't even get one residual plot anymore once you're doing ordinal regression. But you're just checking that nothing funny is going on, and that you've got this linear relationship at each level. So once we're satisfied, and here I am, like I can't see any trends that are going to drive me crazy here. So now we're satisfied with our assumptions. Let's go ahead and draw some conclusions from this model that we fitted before. And here's my confidence interval slide. Just note that you can also get the confidence intervals. You can basically do anything to these ordinal regression models that you can do with other models. So yeah, now I've got 95% confidence interval for the sex coefficient and the old peak coefficient, and that's telling me, the effect of old peak is going from 1 to 1.71, and the effect of sex is, this is a bit funny. I thought sex was negative. So this is probably on the, this is probably the wrong thing. Yeah, I'm not sure what that is. So let's just skip that slide. Because going back to this model, you've got this coefficient for sex is minus 1.42, and this coefficient for old peak is 1.38. So now what I know is that an increase of 1 in old peak results in an increase of 1.38 in the log odds of moving to a higher class. And so what this means is that for each increase of 1 in old peak, the odds of a more severe disease are approximately 4 times higher. So I took this off the log scale because a lot of people can understand multiplicative scales better. And so e to the power of 1.38 is 4. That's where the 4 came from. And yeah, so obviously old peak seems to be quite diagnostic of severe disease severity class. And I've just put here P is very small. So we're quite confident in that result. And also being female is associated with a decrease of 1.42 in the log odds of moving to a higher class. And this means that males are associated with 4.1 times the odds of more severe disease class than females. So I took that off the log odds scale just by raising it to the power of E, raising E to the power of E. And you can plot your model estimates. So this is the kind of thing that comes out of a ordinal regression. It's like instead of getting the mean for each value of old peak, you get 4 predicted values for each value of old peak and male and female. And this is what they are. So this is sort of saying at 0, there's a 75% chance if you're male of being in class 1, having no disease. But if your old peak is 4, then you've now got a 95% chance of being in old peak class 4. And similarly for females. So yeah, I guess I just wanted to demonstrate that predicted values from an ordinal regression are a little bit complex because you get a set of predicted probabilities for each observation. And you could also do it as a heat map instead of that line map. So the probability of being in each class across your predictor variables. This is what was estimated by the model. So the final points are, what can I do if the proportional odds assumption is not met? So if it's just in some variables, you can fit this thing called the partial proportional odds model. So some variables can affect different disease severity classes differently, and you have others which have a single effect. So you could think of these variables that have a different effect depending on what disease severity class you're in as variables that just affect the thresholds. So for the example we've worked through, you could say sex is just something that I'm adjusting for. It's not really a variable of interest. So I could use sex to estimate a different set of thresholds for each, so a different set of thetas for each of male and females. But I still want a single effect of old peak. So I want old peak to affect the odds of being in a more severe disease class. And I just want one effect of that so I can interpret it. And if you did that, this would be the results. You just get one coefficient for old peak it's very similar to what you had before, minus 1.41. It's out in the second decimal place. And sex is no longer in your coefficient estimate. Instead, you get these 3 sex coefficients, 1 at each level. And you probably don't really look at them. You just sort of say, I've adjusted for sex, and this is the effective old peak. For this model, I think the proportional odds assumption held, so you don't really get different results from doing it that way. But for some models, you might need to do this. And then what about the adjacent hazards model? Blah, 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 other things that you've heard of. I haven't gone through these in this talk. Honestly, I think it's a lot less common, and the cumulative link model has handled all the real life things I've come across so far. So just wanted to really focus and nail that one. And yeah, that's the end of this talk. How friendly was this introduction? You can tell me about that later, but here's little ordinal scale to finish this talk on.
Thanks, Eve. So I can see one question just at the end there, and if anyone else wants to ask a question, please jump in. One is from Ordinal. Can you get some kind of marginal effects? I think you're addressing that, but that's the...
Yeah, okay, so you mean the marginal effect of old peak after adjusting for sex, for example? Is that...
I'm not sure, yeah.
Feel free to speak up, Ordinal. But yeah, basically these effects were marginal actually in this model. So this is like a multiple regression where every regression coefficient is interpreted as a marginal effect.
Thanks. Anyone else like to jump in with a question? Okay, well, looks like...
if anyone wants to ask questions later, I feel like the main question is, are you going to share your code? And I will do that. So, yeah. Awesome.
Great.
So sorry, my video is not showing up.
No, that's fine. All right. Well, thanks everybody, and thank you so much, Eve. Awesome presentation. That was great. So until next time.
Thanks, Nick.